Alrighty, good morning or good afternoon, ladies and gentlemen. Today I'm going to go through some sets of notes. We're going to finally look at some math problems. This is all going to be surrounding something called interest. So I'll actually go into what interest is, how it works. These files you can find online. One other piece of good news, I finally have some better audio equipment, so you should be able to have a much better sound quality and hear me talk a lot better. So jumping right in, kind of connecting to what we were doing before, there was the three accounts that we could potentially get. We can get a savings account, we could get a checking account, or we could get what we called a TFSA account, or a tax-free savings account. So this is all from some type of bank or credit union. So as a whole, financial institutions borrow and lend money. That's their main goal. Whether or not this is a loan company or a bank or a credit union, that's basically how they function. So first step, when you invest in a financial institution, you are lending them money for a period of time. So when I say invest, that could be putting money in your account. Contrary to what we kind of think of when we think of a bank, it's not just a vault that we put a bunch of money in and then it just stays there. They use that money for other things. So what we're essentially doing when we put money into a bank is we're saying, hey, we want this back eventually, but for now you can use it however you want. In return, the financial institution pays you interest for borrowing your money. So, whoops, typo, your money. So one good thing is you get paid for having this money in your account. The financial institution then takes the money in your account and say someone else asks for it. So say you put in $500 into the bank, someone comes along the next day and says, hey, I need a loan for $200. They might take the $200 out of your bank account and then lend it to them. Now that's not to say that you can't then go in and take out your $500. They're not going to be like, oh, sorry, there's a couple hundred that's being lent out, because there's lots of people that deal with a bank. But what ends up happening is, rather than paying interest to you, which the bank does, the people who borrow money are charged interest. So interest can be something that goes towards you or is charged against you, depending on whether or not you're lending or borrowing money. One of the things I'll point out, the interest rate that they pay that financial institution is higher. So the person who's borrowing money will pay a much higher interest rate than what the bank will pay you. So because of that, if, say, you are getting 1% interest and the person borrowing money has to pay 5% interest, the bank is going to make a profit. So the key bit, how banks essentially function, is they hang on to money, they keep it safe, and then they lend it out to other people and they charge the people for lending the money out. But they also reward the people who save money, because then they have more money to work with. So there's two types of interest. The first one that we're looking at is something called simple interest, which you'll see is the simpler of the two. So the equation, or the formula that we use, is this one here. So I equals P times R times T, or sometimes you'll just see it written as IPRT. So keep this in mind. This is going to be useful. This will be on any sort of test or quiz that we have. How you break it down, this is the interest paid or owed in dollars. So if a bank owes you interest, you can calculate how much they're going to owe you over a certain period of time. Next up is what's called the principal. This is the amount invested or borrowed. So if you put in $500 into your account, the principal is going to be equal to 500. R, little r, stands for the annual, or another word for annual is yearly, rate of interest. And the key bit is we have to express it as a decimal. So one of the things that's going to be that you're going to have to watch out for is in these questions, you'll see something like a 4% interest rate. We cannot put r is equal to 4. So r is not equal to 4. Instead, we have to change 4% to a decimal. How we do that is we take 4 and we divide it by 100. We drop the percent sign and we get 0.04. So then our r value in this case would be 0.04. Last one, we have t, or little t is the length of time in years. And we use this formula to calculate the amount of interest earned, and the amount of interest is not added to the principal and reinvested. So basically imagine if a bank cut you a check every year for whatever this interest was and just gave it to you. So in order to calculate this, you can calculate interest, no problem, but there is a helpful little triangle that you can use to calculate other things. So what I have is this triangle right here. You may have seen other ones in other classes that were like I and then like 2 letters, but this one has a little bit more. But basically to find any variable, you're going to read this as a fraction. So these, I'll use a different color. These vertical lines, or like somewhat vertical lines, mean multiply. You're multiplying this. If you have this line here, it's the same thing as dividing. So you're always going to kind of read it as a fraction. So for example, say you want to calculate I, you cover up I, and you get P times R times T. So that works for what we have. So I equals P times R times T. That's our normal formula. Say I want to calculate T. So I'm going to cover up T, and then whatever is left is my new equation. So T in this case would be I divided by P times R. If I wanted to look at R, I'd cover up R, and I end up with I divided by P times T. And then lastly, if I cover up P, I'm not going to do it this time, I'll leave it blank, but you can see if you cover it up, you'll get I over R times T. So you're always going to get I in the top, except if you're calculating I, and the rest you can use this handy triangle. So what I often like to do is I tend to draw on my tests, and one of the things I'll draw is this triangle, so I remember what the triangle looks like, and then I just put it on the top of my test sheet. That way I have access to it if I ever have to write a test or a quiz, and I know what this is for. The other thing is you can always calculate the total amount that you have in your account at any one time. There is this new value A, and how you calculate it is A equals P plus I. So if your principal was equal to, I'll keep going with $500, and say you earned interest and you earned $20. The amount that's in your account, so capital A for amount, is equal to P plus I. So it would be 500 plus 20, so it would be $520. Easy. The trick is that you calculate I first and then you plug it into this. So a couple of equations. There's a couple of things that to watch out for, so we'll go into it, but we're kind of keep this I equals P R T in our head. So we want to know the amount of interest that will be earned at the end of the following years. So first up, the rate is 4%. So R is not equal to 4. And I actually calculated it up here. Instead, R is equal to 0.04. So again, I got that by dividing by 100. Following this up, 3 years, so I have I is equal to, my P is 1500. So I'll put P equals 1500 over here. So I have open brackets, I'll make this a bit bigger, 1500 times 0.04 times 3. And this gives us an interest of $180. So notice how it's less than the 1500 because it's just the interest. It's not the total amount in the bank account. This is the amount the bank paid Olive. So technically, if I wanted to calculate how much she would have in her account, I would then add it to this 1500. Well, what happens if we have something like 5.2 years? Well, that's not a problem. I can plug in 5.2. So again, 1500 times 0.4 times 5.2. Because it gives me as a decimal value or as a fraction of a year, that's not a problem. Calculating this through, plugging it into my calculator, I get $312. And because we're dealing with money, it's always a good idea to have this dollar sign so you know what you're talking about. At least if you're talking about the interest or the principal. If you're talking about time, you want to mention years. If you're talking about rate, you could change it into a percent. All right, C, this is where we get our first bit of complication. We have 7 months. So remember, T is in years. So how we do this is same thing. I is equal to 1500, 0.04, but I want to express it in terms of a year. So I know how many months are in a year. There's 12. So 7 months is here, and then 12 months is down here. So I'm doing a unit conversion to convert to this. And the interest rate would then be $35. Last but not least, for question D, 100 days. So again, my time still has to be in years. So now I have I is equal to 1500, 0.04. So that hasn't changed. But now I have 100, and I need to think about how many days are in a year, and I put that on the bottom. So there's 365. And that gives me an interest rate or an interest value of $16.44. So not too bad so far. What happens if I want to calculate something else? So this example says Treya invested a certain sum of money in a financial institution and earned $200 in interest after 4 years. If the annual interest rate was 5%, what amount did Treya invest? So the question that they're asking for is how much did she originally put in? So they're asking what is the principal. So if we're calculating principal, we have our I is equal to P RT. So I'm calculating P is equal to I over R times T from that. And I like to write out all my variables, so I want to be very clear on what I know. So I is equal to something, P is equal to something, R is equal to something, and T is equal to something. So oftentimes what I'll do is I'll set up like a little grid like this. So $200 interest, I'm looking for that word. So $200, I can just put 200 in. 4 years, so T is time and years, so I can put 4. If the annual interest rate was 5%, so I can put 5%, but I can't leave it as a percent, so it's 0.05. So what I did here was I divided by 100, and I'm figuring out what that is. So plugging this into the equation that I've made, I have 200 divided by 0.05 times 4. And how I would solve this is I'd figure out what's on the bottom first and figure out what's on the top, or get this all as one term and then divide 200 by that. But skipping that, I have an answer of 1,000. Principal is in dollars, so principal is equal to $1,000. Okay, next up, Brooke has $2,400 to invest in a financial institution. Calculate the annual rate of interest if her investment was worth $2,700 at the end of 2 years. So I have P, I have R, sorry, little r, and I have T, and I also have another value here. I have A, because what they said was I initially invested $2,400. They didn't give us the interest rate, that's what we're trying to find, and they said 2 years, but they said the whole thing was worth $2,700 at the end. So that's not how much interest I've made. Instead, I have to look at these two numbers. So the interest made would be 2,700 minus 2,400. And how I get that was we had that equation A equals P plus I. So rearranging, I can do I is equal to A minus P. So A minus P is 2,700 minus 2,400, so I is equal to 300. Trying to find out the rate, I'll use this triangle here. So rate is equal to I over P times T. So plugging this in, I have 300 on top divided by 2,400 divided by 2. And you can see we're probably going to get a small number here. So I'm going to get 0.063. I don't want to leave it this because they want the annual rate of interest, so they want this as a percent. So our last step is to times this by 100 and add a percent symbol, so I get 6.3%. And the trick here is that I'm always moving the decimal place over once, twice. All right, last one for simple interest. This is going to be a bit of a longer video, but I'll try to timestamp it so you can see. Wade deposits $5,000 in an account earning interest at a rate of 4.5% per annum. So one of the words you'll see is annum. That means year. So I know right away the principal is $5,000. I know that the rate is 0.045. Calculate the number of days. So they want T in days, and they want an interest rate of, or an interest earned of 360. So calculating time is equal to I divided by P times R. So I get 360 on top, and I have 5,000 and 0.045. If you leave this as a percent, it's going to be much too small. So from this, you're going to get 1.6, and that's not days, because how this equation is set up is time always shows up as years. So beforehand, when we were given days, we had to change it into years. Now we're calculating as years, and we have to convert it back into days. So I have 1.6 years, so there's 365 days per year, so I take 1.6, and I multiply by 365 days, and that gives me a final value of 584 days. So one of the things to always be aware of is what your question is asking. Don't just plug in the formula. What they can do is they can ask for a different time, they can ask for the interest rate, they can rearrange it so that they're including this total amount invested. So you really have to break apart these questions into what they're asking. Next up, pardon me, there's something called the Rule of 72. I'm going to go through this super quick. I'm only going to do a couple of things on this, but this is used to calculate, or it's a fast and handy to calculate or estimate the number of years for it takes an investment to double. So basically, how long does it change for the amount that you have in your account to double. So if you put in 500, how long is it going to take for the rate or for you to get $1,000? It's not exact, but the rule of 72 is a little bit helpful. It's a fast and easy method. So in other words, an investment doubles in value when the interest rate multiplied by the number of years it is held is equal to 72. So the normal formula is R times T is equal to 72. But a couple of things. You leave R as a percent, so you don't change it to a decimal. And don't change this when we deal with compound interest. As you'll see in a bit, we'll talk about number of compounds. Do not change to number of compounds. So what you do, you can cover this up same way. So if you're calculating, say, R, you're going to cover up R, and whatever's left is your new formula. Again, this represents a division. This is times. So R would be equal to 72 divided by time in years, and the time would be equal to 72 divided by R. One thing, does not give an exact value. It approximates the investment value after a given number of years, and it's a simple method of finding out how much an investment is worth without having to use formula or tables. So, example, using the rule of 72, calculate how many years it will take for an investment of $4,000 to at an interest rate of 6% to double in value. So for this one, we're calculating time. So our formula here is time is equal to 72 divided by R. I leave this as a percent, so it would be 72 divided by 6. And from that, I get 12 years. So if you put $4,000 into an account that made 6% interest per year, after 12 years, you could expect to have about $8,000. What interest rate is necessary for an investment of $25,000 to be worth $50,000 in 18 years? So now we have, this is asking the doubling question just in another way. They're not saying the rule of 72, but because this is double, you immediately think rule of 72. And from this, I'm going to calculate the interest rate. So rate is equal to 72 divided by time. So I want 72 divided by 18. And from this, I get 4%. Fun fact. You don't need the principal. So they give you the $25,000 and the $50,000. They also, in the first one, gave you $4,000. Those are a bit of a misinformation because at 4% and 18 years, any investment will double. So if you had $4 in your account, you would have roughly $8. If you had $25,000 in your account, you would have $50,000. If you had $1 million, you would have $2 million. So because of how these interest rates work, this rule is handy for using it on any value. Next example, we're calculating the number of years it would take for an investment to approximately double at a rate of 9%. So time in years is equal to 72 over 9, and that gives us a value of 8 years. So higher interest rate is a lower, or it equates to a lower doubling time. Use the compound interest formula. We're not there yet. So we're going to come back to this one because we're now going to learn about compound interest. So in the last lesson or earlier in this video, you watched and learned how we did simple interest. However, simple interest is different, and so one of the things I'll put is simple is not really what happens. The reason being is, say you have $10 in your account, and at the end of the year, they pay you $1. They're not going to cut you a check for $1 and send it to your house. What they're going to do is they're going to put the $1 into your account. So then you're going to have $11. So then the next year, you're going to get interest on what you have in the bank. You can think of it as your new principal for year 2 is $11. So we've changed the amount. So now we're going to get not $1, but we might get $1.1 in interest. So now we got a higher amount the following year. Few things how this works. If you keep the interest earned invested, the new interest will be paid on the principal amount plus the first year's interest. This is kind of like your A that we talked about. Another way of thinking of it is you earn interest on the interest. This is how both borrowing money and saving money works. So an investment earns compound interest when the interest from each time period is added to the principal and earns interest in subsequent time periods. Because of this, the interest earned grows as well. The longer your investment is compounding, and we say it's compounding every time this year rolls around. So when I make it to $11, that is compounded once. Here, I would have $12.1 after the second year. This is compounded twice. So if you invest for the long term, it is in the last years of the term that you'll see the biggest impact. So how you can think about this is sort of a graph of money divided by time, and you should expect to see it grow like this, or even more so like. So in the last couple years, if you have years here, you'll see the biggest change in the last year. You'll see the second biggest in the year before that, and then at the beginning you don't see much change at all. So the key bit for this is, for us, long-term savings are important. If you start early, it's going to have a bigger effect down the road. I have a video to show you. It's from Futurama. Maybe some of you have seen it. And it gives kind of a good idea for how this works. And maybe we'll actually try this problem.
Crud. We're 50 cents short. I'd love to chip in, but Bender stole my wallet. Hey, that's my old bank. Maybe my account's still open.
We don't seem to have your retina scan, your fingerprint, or your colonic map on file.
Yeah, well, I did open the account over 1,000 years ago. What about my ATM card?
Do you still remember your PIN number?
Sure. It's the price of a cheese pizza and a large soda back where I used to work. Panucci's Pizza.
Okay, you had a balance of 93 cents.
All right.
And at an average of 2.25% interest over a period of 1,000 years, that comes to $4.3 billion.
All right, pretty good, eh? So eventually I'll use that as a little mini lesson to show just how close they were or far away. But the kind of idea is the longer something is invested, even if it's a small amount, will make a huge difference over time. So a bit of a life lesson: the longer the interest is compounding, the greater amount of interest you earn. And the earlier you start saving, the more time there is for an investment to grow. So even the difference of 1 year can make a huge difference. So although it earns you more money when you're investing, compounding costs you more when you're borrowing. So conversely, paying things off over a long time is way more expensive. If you're paying it off, you're going to be paying mostly, if you're paying, say, off a house, most of your first year's payment is going directly towards the interest owed. So you're only paying off that principal just a little bit. So the formula for this, how we calculate simple interest for both paying and like borrowing and lending money is the same. It is this right here. So A equals P, open brackets 1 plus R to the N. So you can see it's a lot more complex than our simple interest. We cannot use a triangle. Couple of changes are we don't see I anymore. We now have this A, which is our final amount, and that is equal to principal plus interest. So it's the same A as before. Principal, the amount invested or borrowed, we still need to know. The annual interest rate, again, we express it as a decimal. And then there's this new one. There's this number of compounding periods. So this is amount of times in a year interest is reinvested. If it happened at the end of every year, then you would get interest on the principal once, they would calculate it, and then that would be reinvested. If it happened every month, at the end of the first month, you would have a small chunk of interest paid to your account, or you would owe, and then that would be reinvested for the next month. So a couple of things, there are different time frames for the compounding interest. Is annual, so number of compounds per year. Annual means 1. Semi-annual, semi means half, so this is half a year, so there's 2 periods per year. Quarterly, we split it into quarters, so there's 4. Monthly, there's 12. Weekly, there is 52, so there's 52 weeks in a year, and daily, there's 365. This is important for us to know. All right, so going into how we can calculate simple interest versus compound interest. So this is part of our compound interest. So first example, we're just going to compare simple interest. So they want us to do a simple interest problem. So the question is, Jenny invests $5,000, so her principal is $5,000. And the rate is 6%, so 0.06. Per year, simple interest, calculate her interest at the end of 3 years. So T is equal to 3, and they want to calculate I at the end of 3 years. So I is equal to P times R times T. So I is equal to 5,000. Sorry, I'll make this bigger and a little bit more clear. 5,000 multiplied by 0.06 multiplied by 3. So this gives us a value of $900, which isn't bad. $900 is pretty good. The question wasn't asking how much interest though, they asked about the total amount, so I have to use my A equals P plus I. So my A is equal to 5,000 plus 900. So in total, her investment is worth $5,900. Pretty good. That's using simple interest. So let's see how much more it would be with compound interest. So on the next page, we're going to complete if the interest rate was compounded once per year. So investment value, how you would make a table like this is at the beginning of the year, how much did she invest? So she had $5,000. The interest rate is 0.06. Interest earned, I calculate 5,000 times 0.06. Because the number of years is 1, I can leave it out, but this gives me 300. So I earn $300 at the end of the year. So then the investment value at the end of the year, so this is how we are starting with compounding. So we add together 5,000 plus 300 to give me $5,300. So the new amount that she's going to invest, I take this and I put it in here. Because at the start of the second year, she's going to have $5,300 in her account. Interest rate has not changed, but now the interest earned, I'm going to calculate from this. And I'm already making a mistake, or I'm not making a mistake. Again, 1 year, I'm going to leave the 1 out. This gives me an interest of $318. So then the total amount invested is now $5,300 plus 318. So she's now made $5,618. So already a little bit more, but let's be sure, because this is still less than the end of the 3 years. I'm going to take this value and put it in here. So I now have $5,618. My interest rate has not changed. So now my new calculation is $5,618 times 0.06, and that gives me $337.08. Super important to include the 8 cents. And we add this all together, so we have 5,618 plus 337.08, and this gives me a final value of 5,955.08. Alright, well, I don't want to make a table every time, so this example is calculate the amount of interest, or how much the amount is worth at the end of the year, but now we're going to use the formula A equals P, 1 plus R to the N. So one of the things you're going to need is on a calculator, you need a power symbol, because this is not always going to be 1 or 2, it's going to be a different number. So on a calculator, the button sometimes looks like this, or it'll look like that. It also might be a second function where you have, like, if you've got like one of those fancy scientific calculators with like, sometimes they've got like a directional arrow, there's usually like a second function button, and then you'll see something that's like x squared, and then underneath it, or not on a button, but in writing, it'll say like y to the x. So you might need to press second function and then that button to get it to work. But if you're running into problems with your calculator, let me know. I don't know what A is. P, I start with 5,000. R is 0.06. N is the hard one. How many times was it compounded? So it's compounded annually. So we're following the same thing once per year, and it's over the span of 3 years. So 3 times 1 is equal to 3. In this case, it's not so bad. Alright, solving this, A is equal to 5,000, 1 plus 0.06 to the power 3. So how we solve this, remember our order of operations. I do everything in the brackets first, so I have 1.06. I take this to the power 3, and then I multiply by 5,000. And that gives me a value of $5,955.08, which is exactly what was given from this. So really, compound interest is just simple interest, but with more steps and different values each year. However, if you're doing this for like 10 years, I don't want to make a 10 deep table to make this work. Instead, let's just use the formula. Next example is how much more money did Jenny earn while it was compounded? So comparing $9,955.08 minus 5,900 equals $55.08. So even with only 3 years, we haven't changed anything. She earned an extra 55 bucks. So always, always, always compound interest is better, and we never really see simple interest. It's usually generally calculated as a compound interest. Maybe if you're making monthly payments on something like through a payment plan, they'll calculate everything as simple interest, but banks want to make the most money, so if they're charging you interest, they're going to want to do it compound, and they don't want to cut you checks for like 10 cents every time you save up per month, so they just put it back into your account, which makes the same thing. So let's try 2 more examples and then we're done. So Viola invests $1,000 at 10% compounded annually, and how much will it be worth after 8 years? So A, I don't know how much it's worth. P, she invested 1,000, and I is equal to 10%, so that would be 0.10. And sorry, this is R. And finally, N is equal to, well, compounded annually, so once per year times 8, so that gives me 8. So my formula that I can plug in is A is equal to 1,000 times 1 plus 0.1 to the power of 8. So you can see right away we're going to need that power symbol on our calculator. 1,000, 1.1 to the power 8. So this gives us a value of $2,143.59. So already more than double. If we want to calculate interest, it's A minus P. So this gives me a value of $1,143.59. So she's earned over double in just over 8 years. Sorry about that. One more example. Bob invests $2,500 at 7.1% compounded monthly. Calculate the amount of investment after 5 years. So A, I'm looking for, I don't know what it is. P is 2,500. R is equal to 7.1%. So that is equal to 0.071. And N, compounded monthly. So this is 12 months in a year, and there's 5 years, so it's 12 times 5, which gives us 60. So plugging this in, I now have A is equal to 2,500, 1.00, and I apologize, there's one more step that we need to do here. So 1 plus, this is the yearly interest rate. So because it's compounded monthly, they also split the interest. So the monthly interest, I'm also going to divide by 12. And this gives me a value of 0.0059. So it's a much smaller number. Be sure that you're catching that, because otherwise you're getting not 7.1% a year, you're getting 7.1% per month, which is a huge difference. That would probably have blown up our calculator. So one way you can check, anything to the power 60 is going to be a huge number on our calculator unless it's very, very, very close to 1. So one of the things you can look out for is if the person's invested something for like 5 years and they've invested like $2,000 and suddenly they're getting like $3 million, there's something terribly wrong. You've probably made the mistake that I almost just did and not divided out. So 1.0059, this is very close to 1, so we're not going to get a huge number if we punch that into our calculator. Remember, do this chunk first. I'm kind of showing you all as one step, but once you figure this out, or once you go through this, it'll be $3,558.18. I'll stop here. I'll show you the rule of 72 in a little video with compound interest just to compare. But what I recommend doing, if you have a calculator at home that you're going to be using for quizzes and tests, try some of these out. Make sure you're getting the same numbers that I am so that you can see that you're making the right steps and you're not putting them in the wrong order. If you find you're getting answers wildly different, probably what's happening is you're multiplying 1,000 to this first, or you're adding something up wrong, or you're forgetting to divide by months. So just be careful. There's a lot of finicky little bits in this that we need to be aware of. So as always, take care, stay safe, have a good one. The assignment will probably come out tomorrow for this, and you can try this out on your own. All right, have a good one.